The idea that red, yellow and blue are primary colours that can't be created by mixing remains widely held among many artists and art teachers. In this extract from a recent conference presentation, I suggest where this idea may come from and why it remains popular despite frequent criticism. The defining tenet of traditional colour theory, as expressed in the traditional colour wheel, is that the so-called primary colours red, yellow and blue can mix to produce other colours but can't be created by mixing other colours. This idea of red, yellow and blue primary colours has been widely criticised as scientifically incorrect, but it actually isn't completely inconsistent with current science. In science, it's generally accepted that hues such as red, yellow and so on are perceptions created by our visual system, and a very widely, though not universally accepted theory, holds that there are just 4 hue perceptions, the unique hues, red, yellow, green and blue, that we perceive as pure and unmixed with other hues. For example, we can all imagine a yellow that's somewhat greenish and another yellow that's somewhat orangey, but somewhere in between we can imagine a unique yellow that's neither orangey nor greenish, but just yellow. And we can arrive at unique red, unique blue and unique green in the same way. Our other hue perceptions can be described as intermediates between adjacent pairs of these 4 hues, as shown in the NCS hue circle on the left and as described in the passage by Ewald Hering on the right. The red, yellow and blue primary colours of traditional colour theory are typically defined and understood as pure hues exactly like the red, yellow and blue unique hues of science, except that these primary colours are imagined to be present in our paints instead of in our minds. In split primary versions of traditional colour theory, paints representing warm and cool versions of each primary colour are imagined to contain the primary colour plus an impurity or bias of an adjacent secondary colour or another primary. But unlike the unique hues, traditional colour theory excludes green from the primary colours, typically because green is considered to be made of yellow and blue. This idea comes from observing that we can easily create green mixtures from yellow and blue paints, and imagining that the colours of our paints are located in our paints and are mixing there. Yet if we mix lights of the same 2 colours, we get a white mixture. And if we intersperse stripes of those colours, or if we rapidly spin 2 discs of those colours, we get a grey mixture. So what's going on? Why do blue and yellow sometimes mix to make green, sometimes white, and sometimes grey? What's going on is that it's not the colours that are mixing. These are different physical processes whose products have different spectral properties that evoke different colour perceptions. It's only a dilemma if we think it's the colours yellow and blue that are mixing. The colour of a paint is our perception of the spectral reflectance of the paint, the proportion of each wavelength of light that the paint reflects. And the spectral reflectance of a paint mixture is the result of a complex physical process that involves an important subtractive component. The yellow colour of our paint is the way we perceive a spectral reflectance that's high for long and middle wavelengths and low for short wavelengths, and the blue colour of our paint is the way in which we perceive a spectral reflectance that's high in short wavelengths and some middle wavelengths. In subtractive mixture, the wavelengths that are in common survive, so we're left with a small predominance of middle wavelengths which we perceive as green. This has been understood in science since it was clearly explained by Hermann von Helmholtz in 1852. We can even get a green mixture from a blue paint that's not at all greenish and a yellow paint that's not at all greenish. The traditional colour theorist imagines these two paints as not containing any green, and understandably concludes that the colour green has been created by mixing the colours yellow and blue, and so rejects green as a primary colour. This doesn't happen with red, yellow or blue, because we find in practice that we can't make a red mixture without using at least one paint that's already reddish. We can't make a blue mixture without using at least one paint that's already bluish, and we can't make a yellow mixture without using at least one paint that's already yellowish. We can mix a violet paint and a blue-green paint to make a blue mixture, but the traditional colour theorists can say, no, I can see there's already blue in that violet paint, and we know that green is made of yellow and blue. So there's plenty of blue already in those paints, so you haven't created blue by mixing. Shortly after the conference where I presented these slides, some perfect examples of this kind of reasoning appeared in these comments on an Instagram post in which painter Ken Goshen demonstrated a bright blue mixture obtained from quinacridone magenta, phthalo green, and a white paint. Of course, we can also easily explain getting these blue mixtures in terms of spectral reflectances. Violet and magenta paints strongly reflect long and short wavelengths. Bluish-green paints strongly reflect middle and short wavelengths. So subtractive mixture results in a predominance of short wavelengths that are in common, which we perceive as the colour blue. We can make a red mixture from a magenta and a yellow paint, but the traditional colour theorists can say, no, you haven't created red by mixing. There's already red in that magenta paint, I can see it, plus a bit of blue or violet. What's happened is that we've got some red, yellow and blue, and everyone knows that that makes black, and extra red left over, so we get a red mixture that's a bit dirty. Again, the spectral reflectance explanation is also intuitive. Our magenta paint strongly reflects long and short wavelengths, and our yellow paint strongly reflects long and middle wavelengths. So subtractive mixture results in a predominance of the long wavelengths that are in common that we perceive as red. And we can make a kind of yellowish mixture by mixing a yellow-green and an orange paint. But for the traditional colour theorists, the green gold already contains plenty of yellow, and orange is made of red and yellow, so the yellow is already present in both and has not been created. Explanations of this sort, based on the understandable assumption that the red, yellow and blue unique hues that we perceive in our paints actually reside and mix in those paints, seem to be flexible enough to appear to explain any mixture of paints without disturbing the tenet that red, yellow and blue cannot be made or created by mixing other colours. By rejecting green and arranging the remaining three unique hues symmetrically, we end up with a distorted colour wheel that's very uneven perceptually, changing very slowly between yellow and red, and very rapidly from yellow to blue. And if red, yellow and blue are taken to be the unmixable components of all other hues, it's disappointing to discover that a middle red, middle yellow and middle blue paint mix a rather restricted and very uneven range of colours, reaching high chromas for orange, but much lower chromas for middle green and purple. And it's difficult to explain why paints of another set of hues, cyan, magenta and yellow, mix a larger and more even gamut. But these issues don't sway the traditional colour theorist, for whom the appeal of primary colour theory isn't founded on perceptual spacing or gamut size, but on the fact that it seems to provide an intuitive explanation of paint mixing. Primary colour explanations and spectral explanations can both seem to account for paint mixing, though only the latter describe what is actually happening in our paints and can be applied quantitatively to predict the precise hue, lightness and chroma of a series of paint mixtures. It could be argued that the primary colour explanations work well enough for practical paint mixing, and it's true that there are many extremely fine painters who use this approach. But even if we accept this, to understand many other things about colour apart from paint mixing, students will still need to understand that these primary colour explanations are imaginary, that it's not the colours that are mixing, and that the colour green isn't really made of yellow and blue. If you'd like to see a slightly fuller version of this presentation, including a reference to the history and a recent criticism of the idea of the unique hues, you'll find it in this presentation I gave for the Colour Society of Australia National Conference, which is available as a video and an illustrated PDF at these links. Thank you.